Welcome back to the Building Science for Dry Climates video series with Franklin Energy. This video is part 3 in the Building Science series, and our focus today will be on combustion safety. In this video, we're going to look at combustion safety and the critical role that it plays in maintaining safe and efficient homes. So what is combustion safety? The best answer for that should start from the house as a systems point of view. When you begin to look at the house as a set of independent systems that can and do affect one another, you can begin to see how changes to one aspect of the house, like say the air barrier, can cause changes in other aspects of the house, like indoor air quality and moisture movement. When we air seal and insulate a home, we change how that house operates. Our biggest responsibility as building performance contractors is to ensure that safety of our clients. Every home should be tested and inspected for safety before heading home every evening, in case there are potentially lethal conditions. Dangerous conditions can arise quickly when a home with combustion appliances is air sealed and before pressure imbalances have been addressed. What are some of these potentially lethal conditions? Well, when you make a house more airtight, you can also make existing problems worse or even create new problems. Small amounts of carbon monoxide or even tiny gas leaks that might not have been problems when the home was still leaky will become new problems if those issues aren't addressed after sealing the home. In addition to the buildup of gas leaks or carbon monoxide, other potentially lethal conditions can arise from depressurization and backdrafting natural draft gas appliances like water heaters or older furnaces, which can also lead to spilling combustion byproducts into the living space. Air sealing a home also traps in moisture that probably used to get flushed out through previous amounts of shell leakage, and the newer, higher humidity levels can lead to potentially harmful mold as well. So what are we looking for when we're talking about combustion safety? Combustion safety includes both visual inspection of and diagnostic testing on all the parts of the combustion appliances. It also includes identifying the area or zone that those appliances are located in. Visually, we're looking at the condition of chimneys and vent pipes, maybe the existence of even small fuel leaks, or even checking like the condition of the wiring. If we can test the heat exchanger either visually or with carbon monoxide testing and supply air. And as you're doing all this, you ought to be paying attention to the ductwork, even the location of returns and supply registers. When we're looking at inspecting chimneys and vent pipes, we're looking for things like rust. Are the holes, is it falling apart? Does it have its mechanical screws holding it together, or is it twisted to get together correctly? About chimney blockages. Is it too short? Is it too large? The diameter or even the upward direction of a pipe. So we also look at even masonry chimneys and look for things like maybe, does it even need a liner? Clear where the air is supposed to go, but air follows the path of least resistance. That whitish residue on the pipe shows where flue gases have been escaping into the attic. Hell, somebody left this vent completely disconnected. You can even see the draft hood back there in the background. Unfortunately, we run into all kinds of stuff like this in the field. A quick visual check of a chimney can tell you if it's blocked by anything or if it has an appropriate liner if needed, because you never know what kind of conditions you might find if you didn't look. We also check gas lines for fuel leaks. It's common to use an electronic gas sniffer or combustion gas detector to check for gas leaks at all accessible gas lines. Leaks that get detected by the device are then checked with a bubble solution, and even smaller fuzz leaks should be reported and fixed. What we see here in the picture on the left is definitely more than just a fuzz leak. Keep an eye on the condition of wiring. Look for potentially even burnt or scorched wiring. Be familiar and aware of the existence of knob and tube, especially if you're doing attic insulation work. Look for places where the insulation on the wiring can be compromised. Things like, are the heating systems, do they have their own circuits, and are the thermostats run correctly? Inspecting the heat exchanger. While this is a little trickier on newer furnaces, older furnaces can be examined visually for rust and corrosion. You can even watch for the flame to dance around a little when the fan kicks on. With newer models, you can check for carbon monoxide in the air supply, measuring at the closest supply register. Here's something you might be able to see on an older furnace. Carbon monoxide will leak from cracks like these and taint the indoor air. Your visual inspection should also include the ductwork. In doing a duct inspection, you get an idea of how the entire system works by noting the locations and sizes of return supplies. Watch for things like return grills in combustion appliance zones. Is the filter slot too big or uncovered? Filter slot won't be effective if there are gaps for air to bypass the filter. Is there even a filter installed, and what condition is it in? And even see if the air handler fan is clean. If the air handler fan is dirty, the filters aren't working, and the fan can't be as effective as it should. This picture shows a unique type of access to the air filter, not one that we would recommend. It also seems to have a return grill right there next to the furnace. Older furnaces were extremely susceptible to backdrafting in this type of scenario, same as if there was a natural draft water heater in the same location. Here's a closer look at that same photo. As you can see, air will get around that filter, which is not the best case scenario. Poorly placed filters, like the ones we just saw, or systems that have had the filter missing, can create this type of problem. The dust buildup on the fan indicates an ineffective filter. Clean the fan, replace the filter. Let's transition away from the visual inspection component and into the diagnostic testing requirements for combustion safety. When we taught this class in person, I told all of the attendees to fold the corner of this page in their book or earmark it with a sticky note, somehow make it easy to reference in the future. This is the list that summarizes all of the combustion testing procedures in one place. In my own learning process, seeing all of these together was the way that I really began to understand the broader picture about the effects of air sealing a home with the intent to save energy, but the unintended consequences of trapping in potential contaminants like carbon monoxide or increasing the effect of depressurization from little things like bathroom fans and kitchen fans. The significance of these new levels of depressurization is that it can be enough negative pressure to overpower a water heater's ability to draft its combustion gases out of the home. So here it is. Here's what we test. We test for ambient carbon monoxide at the center of the house. We diligently check all fuel lines for fuel leaks. We confirm or check that there's an adequate combustion ventilation air for each of the combustion appliances. We even set up the house in a purposeful depressurization to check to see if these natural draft appliances can indeed draft. We'll also check ambient carbon monoxide at each appliance. We'll check the flue levels of carbon monoxide at each appliance, and noting that the carbon monoxide level for the kitchen appliances each has their own ambient and flue level as well. Taking a look at the specific ways we approach each of these diagnostic tests, when it comes to testing ambient carbon monoxide, we use personal CO meters. There are two common types shown here, but we wear them at all times. Got to make sure it's zeroed out, before entering the house. We're purposely looking at it regularly and recording unusual readings, understanding that any time is greater than 35 parts per million, it's worthy of making a note, and even best practice is to notice why should it even be above 10 parts per million carbon, ambient carbon monoxide. We have a multitude of triggers that we look at for NGAT and PG&E. The fail level is at 26 parts per million or greater. You hit that, you got to turn off the appliances and let the house ventilate. And if by chance you get it at a level of greater than 70 parts per million ambient carbon monoxide, you got to evacuate the house. However, you can continue testing other appliances once it gets down back below 70. For fuel leaks, we're using those electronic gas sniffers, and we're sniffing from the meter to each appliance. Yes, that's right. It's all accessible gas lines, not just the easy ones. A reading or an audible, siren that detects, it doesn't necessarily mean you've got a big leak. So we check with a bubble solution. And if the bubbles begin to percolate or even expand like what you see in the picture, you got problems. Oftentimes, though, even when we check with bubbles, it's actually not enough to create, bubbles. So be mindful and diligent about it. We also are looking for ambient gas readings at each level of the home, and be aware of and call PG&E if appropriate. Combustion gas detectors, often referred to as gas sniffers, have to meet the following criteria. They need to be intrinsically safe. What that means is that they don't have sparks, in their electronics that could, potentially ignite in a combustible environment. They also have to display a lower explosive limit and provide an alarm if that atmospheric level exceeds 10%. They got to be able to produce that audible tick rate that can change and it speeds up as it begins to detect more concentrations. And then, of course, it has to be able to zero out when it's outside. Obviously, it should be calibrated to be current with its own manufactured specifications. Determining if an appliance has proper combustion ventilation air starts by figuring out if the area would be considered a confined space based on the code requirement for 50 cubic feet per 1,000 BTU input of all the combustion appliances in that area. If you have adequate volume of air around the combustion appliance, meaning you exceed that 50 cubic feet needed, then CVA is not required. If it is determined to be confined space because it doesn't have that volume needed, then you pick one of the 4 rules provided to provide venting strategy to get adequate combustion ventilation air to the appliance. CAS testing, or combustion appliance zone depressurization, is a critical part of both the building performance and weatherization industries. We identify the zones of the home that have combustion appliances with the purpose of testing those zones to see how much negative pressure can be created. When you have measured and compared your way into what you know is the worst case depressurization, then we fire the combustion appliances to confirm that all of the combustion gases are still able to vent out and are not spilling or being backdrafted into the home. With the combustion appliance zone in the worst case depressurization, we follow the testing protocols on how to test each appliance for proper drafting. When you fire the individual appliance, if you do detect the spillage of combustion gases, the appliance gets a few minutes to overcome the depressurization and start drafting appropriately. You can see here that under the Building Performance Institute, appliance fails at 2 minutes if it's already a warm vent, or 5 minutes, assuming you're starting with a cold vent. And PG&E's specific rule is if that appliance cannot begin to draft properly after up to 5 minutes, once it exceeds that mark, if it's still not drafting, then it fails. When we air seal a building and make the home more airtight, the effects of those exhaust fans and air handler become more significant on the operation of natural draft combustion appliances. And we are required to test for their safe operation when our air sealing or duct modification work is done. Earlier in the presentation, we showed the slide that had all of the combustion testing items listed on one page. The last 3 of those were about how and where we measure for carbon monoxide at various combustion appliances. They were testing for ambient carbon monoxide at an appliance, combustion carbon monoxide inside the flue, as well as kitchen appliance carbon monoxide and measuring ambient and flue gases. This slide introduces us to the importance of understanding the difference between air-free measurements versus as measured. The easiest way to remember is that air-free measurements are assuming that there is no ambient air mixed into the sample of air being analyzed. Lastly, understanding the location of where the sample, the gas, depends on which type of appliance. Natural draft appliances are sampled in the flue before the draft diverter, and where sealed combustion and direct vent and even induced draft appliances are measured at the vent termination. There are also some exceptions. If you can't get on the roof to sample a vent termination, one option is you can drill a hole in the vent, and that's kind of on you as a contractor. And lastly, at the bottom, you can see that if none of this is feasible, you can actually take an as measured reading at the closest supply register, and that could also count. The tool that we use for measuring carbon monoxide levels are called combustion analyzers. And here are some key functions that they need to do to meet current building science standards. They've got to be able to display the combustion carbon monoxide digitally, calculate and display carbon monoxide as air-free, as well as measured. And they've got to have specific resolution and accuracy. They've got to have a NOx filter, and of course, they've got to remain calibrated to manufacturer's specifications. After a certain amount of time, these need to be sent back to have them recalibrated. This slide was purposely left in despite the age of the picture and the specific type of combustion analyzer. It shows an older model combustion analyzer that does not have the ability to read air-free. Here are 2 examples of more modern combustion analyzers that can differentiate between as measured and air-free measurements. If you're new to all this, we don't expect you to be an expert now that you've seen a video. It's important at this point for you just to understand that there is a difference. Air-free carbon monoxide testing is sampled from a location prior to the introduction of any ambient air. The technician in this picture is sampling the flue gases prior to that barometric damper on this oil furnace. The sample location ensures that no ambient air in the gases is being analyzed. Our kitchen appliances and gas log fireplaces use as measured readings on the combustion analyzer. For the location, where to sample the air, and acceptable amounts of carbon monoxide vary from one appliance to the other. So check the BPI and PG&E documents for those limits and locations. In conclusion, it's important to make the connection between building performance, air sealing, and combustion appliance safety. And that combustion safety includes both visual and diagnostic inspections. Second, there are lots of things that can contribute to unsafe levels of carbon monoxide, including but not limited to negative home pressure, blocked chimneys and combustion appliance venting, and even insufficient combustion ventilation air. Using the combustion appliance zone depressurization testing and checking for spillage can shed light on potentially dangerous conditions that you might have created with your well-intended air sealing work. And lastly, to consider the ductwork, filters, and the air handler unit in your combustion safety analysis. Think of the potential of the air handler unit to create either positive or negative pressures throughout a house, as well as the potential to leak gas at the furnace or even add carbon monoxide into a living space. All of these topics are important to consider when testing for combustion safety. Thank you, and I hope you join us for the other videos in the Building Science for Dry Climates video series.